Quite a few of you are here. Uh, so let's. So I just wanted to ask. Okay, only four of you are here, but like the last class test that I took, only three of you submitted. So like, what was the issue? Was it because none of you could attempt any of the questions, or was the time too short for the four of the questions, or like you had some technical issues submitting? Can any one of you unmute yourself and speak up? Hello? Okay, someone wrote something on the chat. Okay, Medhajit did. Okay, I understand. Okay, so this is your first class, so then don't worry. Then I am asking this question to the rest three of you. Shagnik actually submitted. Okay, that's okay. And what about Devik? What about Devik? Uh,
So this is my first class, sir.
oh, so both of you is the first. Okay, then let's continue then. So for those of you who is attending my class for the first time, I took a class test last week and like it had 4 questions. So let's quickly discuss them first, then we'll move on to next things. So the first one was you had to find the number of zeros at the end of this number, 592 factorial. So this number is basically the product of the first 592 numbers, like that's the definition of factorial. So it's like a huge number. I mean, there are probably less atoms in the universe than this number, so no way computing this. So we are only left with number theoretic techniques to find the number of zeros, number of trailing zeros of this number. So like this number will be something like whatever dot 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 something, and then it will end at some zeros. Why am I so sure that this will end with some zeros? That's because you see, for 1 factorial is 1, 2 factorial is 1 times 2, that's 2, 3 factorial is 1 times 2 times 3, that's 6, and similarly 4 factorial is 1 times up till 4, which is 12. Starting with 5 factorial, we have zeros, like 5 factorial is basically 4 factorial times 5. Sorry, 4 factorial is 24. 5 factorial is 120. Right, so 5 times 24 is 120. I hope you're getting it. So, and since 6 factorial is actually 5 factorial times 6, and 0 times anything is 0, it's 720. So you see, as we go on, the number of zeros at the end of n factorial goes on increasing. So what determines the number of zeros at the end of a number? So 0 is basically a multiple of, like if you have a number n equals to some xyz, these are digits of course, with some k zeros at the end, this implies 10 power k divides that number. Right, so 10 means 10 divides that number only and 100 doesn't. But if there are k zeros, 10 power k divides that number. And 10 is only composed of 2 prime factors, 2 and 5. So 2 power k divides n, and 5 power k divides n simultaneously. So we can use this fact, and the reverse is also true. Like if 2 power k and 5 power k divide n, then 10 power k divides n. That means there are 10 zeros at the end of n. So here we have a number, 592 factorial. So we will just check for the number of factors of 2 and the number of factors of 5 in this number 592. Now you actually don't need to check for the number of factors of 2 since 2 is pretty abundant. Like when you talk about n factorial, so 2 comes more often than 5, so 2 is more abundant than 5. So this the top one is actually more than the bottom number, so we just check for the factors of 5. So what is the general way to find the number of factors of say suppose a prime factor p in n? So the number of, by the way, this is the notation for number of. So the number of prime factors, or should I say number of factors p in n equals floor of n by p plus floor of n by p squared plus floor of n by p cubed plus dot dot dot. So what is this thing like? So floor is nothing but this is called floor. Sometimes it's also called like Dirichlet's function, a box function. So the notation varies from author to authors. Most of them use this notation, the third bracket with a distinct kind of third bracket with the top nudges off. And some authors use the normal third bracket, it's easier to type. And others might explicitly write box of, okay, so box of floor of something. So whatever, whenever we take box of any number n, you you basically round off that number to the nearest integer on the left. Okay, so let's see what it actually means in practice. Right. Okay, so say suppose you have a number. So this is a number line. You have 0 here, -1 here, minus +1 here. This is +2. Let's talk about, let's take the number 0.54, located somewhere between 0 and 1. So when you consider the box of 0.54, this basically returns 0, since the number just to the left of 0.54 and which is an integer, that is 0, right? So like simply the box of 1.2 is 1, since 1.2 is here and the integer to its left is 1. Remember, it's the integer to its left. So the nearest so by that definition, if you have an integer inside the box, right, like box of 2, it actually equals to the same integer 2, because 2 is itself the nearest integer to 2, right? And what if you have a negative number like -1.54? So it's somewhere here. What's the integer to the left of it? -1, right? So it's -1. So I hope this box function is clear to you. So we have some properties of box functions. We may discuss it some other day. So for now, this much is enough. Yeah. So anyone, any doubts? Oh yeah, sorry. Mohit. Sorry. Medhajit. Yeah. I pointed out minus 1.54 wrong. Thank you for pointing out the mistake. So minus 1.54 is located here between minus 1 and minus 2. And that means when you take the box, it's minus 2 and not minus 1. Sorry for the mistake. Thank you. So the number of factors of p in an integer n equals n by p, like sum over n by p power I runs from actually 1 to infinity, since as we go along, eventually p power I will exceed n, and then all the corresponding floor function will return 0, so it won't be a problem. So let's see some working examples. So say suppose 12. So we want to find the number of prime factors of 2 in 12. So then the expression looks something like, right, and so on. But as you can see, after the first three terms, all of them just go to 0. So we can ignore the rest of the terms. So the first term is 12 by 2, it's exactly divisible by 2, it's 6. And 12 by 4 is 3. And this is not exactly divisible, it's 1 point something obviously, and which after taking floor we get 1. So it's 3 plus 6 plus 1. So it's 10. Right, yeah. I'm not actually giving that factorial. Sorry for that, actually. So I wanted to say the number of factors of p in n factorial, right? Not the number n, obviously. So, so this is because you can visualize the numbers from 1 through n as like 1, 2, 3, and up till n. And then if we are trying to find the number of numbers which are divisible by p, the prime factor, then they are exactly p apart, right? Like the number of the multiples of 2 are p apart, 2 apart. So number of such numbers must be strictly less than n by 2. That's why we're taking floor to find the numbers which are divisible by 2. And then when we are dividing by 4, we are trying to get an estimate of the number of numbers divisible by 2 squared. And since we already counted 2 once, we will be only counting the number of multiples of 4 once, not twice. Although 4 is actually divisible by, like 4 has two factors of 2, but still we are counting it once, since one set of 2's are already counted up here. So So here in our problem, we have the number 592, and we want to count the number of factors of, so the number of factors of 5 in 592 factorial is equal to, using our formula, it's divided by 592 divided by 25, and so on. So you can do it in a compact form by a similar kind of technique that we once used to do in our junior classes while converting a number into a different base. Like we used nested divisions like this. Like first we divided it with 5 or whatever the base is. So 5 ones are 5, then 9, then 5 ones are 5, then 42, so 8. So we are left with a remainder of 2, which we used to write here as a side, but we don't need that, so whatever. I'm just ignoring it. Next we again divided by 5, so it's 2 times, so 18 and 3, getting a remainder of 3, which we will ignore for now. Then 5, 3, ignored, and it doesn't go with 5. So these are the corresponding values of the first floor, the second floor, and the third one. So then this basically evaluates to 118 plus 23 plus 4. And if you add them up, you get 140. Right, like 141 plus 4, 145, right? So it's 145. So the number of zeros at the end of 592 factorial is 145. So I hope the calculation is clear to everyone. Like, it was the easiest one of the 4 problems, and I even gave a hint on how to uh, find the factors of 5 in 592, but still only 2 or 3 of you could do it. So I guess we need to stay like focus on easier problems more before moving on to advanced theorems and all. So any doubts, anyone? If not, then I'm moving to the next problem. Before moving to the next problem, since it's the most difficult of the four, so let's first discuss 3 and 4 first. So the third one was you had this quadratic of the form x squared minus 3x minus 1. So this quadratic, and you had to show that 690 that 169 never divides this number x squared minus 3x minus 4. So this is basically means that is 169 never divides x squared minus 3x minus 1 for all values of x in natural numbers. So this is the notation of natural numbers. I gave a PDF with the list of notations that I most commonly use. I will repost it for those of you who have just joined in. Okay, just a second. Okay, so so this is exactly similar to one problem that I discussed, I guess last week in class. So that one was, okay, let me move back to that problem. Yeah, so this one is the problem. So there you had to show that 121 doesn't divide n squared plus 3n plus 5. So you see, you can see the pattern, right? So the divisor in these kind of problems is a perfect square, and the quadratic, whatever it is, can be factorized in this clever way, with one factor exactly divisible by whatever square this number, the divisor is, and the other one can be factored into two factors which are exactly that number apart. Like here in this case, it was 11. And then we had a string of arguments that ultimately resulted to the contradiction. So here, let's try and factorize it. So first observe that 169 is 13 squared. So of course we have to find a multiple of 13 and then two factors which are exactly 13 apart. So keeping that in mind, let's try out with each of the factors of 13. Actually, we have to try it out for each factors of 13. But here, it will take some time with trial and error to find that exact factor. So as I have posted the problem, so I know the factorization. So we can just quickly move on to that factorization. So here in this case, we have the factor as 39. Okay. And the factors which are exactly 13 apart are actually x minus 8 and x plus 5. So you see the quadratic from the first term that we are getting is x squared minus 3x minus 40, and then adding 39 with it will give minus 1. So these two quadratics are seen. Now we have the number expressed in our required format. We can proceed with a line of arguments. So the first argument is, we are assuming for the sake of contradiction. So assume for the sake of contradiction that 169 divides the quadratic, like just this quadratic or this one or whatever, same. Now we will eventually hit upon a contradiction. So now this implies, our assumption implies 13 divides the same thing. Okay, let me write it down. So 13 divides x minus 8 and x plus 5. And that implies observe that 13 divides this next term, right? 39. So 13 divides x minus 8 times x plus 5. Why is it true? Since we have this. If 13 divides a and 13 divides b, then that implies 13 divides a minus b. So we knew 13 divides uh, x minus 8 times x plus 5 plus 39, and also we knew 13 divides 39, so that implied 13 divides their difference, which is x minus 8 into x minus 5. Got it? So now we have 13 divides the first two factors. Now you see 13 is a prime number. 13 can't be distributed in these two factors, right? So 13 has to either divide x minus 8 or 13 divides x plus 5. In any one of the case, the the other will imply. Why is it true? Same reason. We can add 11 on 11 with the dividend, to like still get it divisible, not 11, sorry. We can add 13 in the dividend to still get it divisible by 13, right? That means we can add, we can write 13 divides x minus 8 plus 13, which is 5, x plus 5. And similarly, 13 divides x plus 5 minus 13, which is same as x minus 8. So in any case, 13 divides both the factors. So 13 square divides their product. Similarly, 13 divides x minus 8 and x plus 5. I mean 13 square divides x minus 8 and x plus 5. So now we have the first term divisible by 13 square is 169. So 169 divides the first term. So this is what we inferred from our line of arguments. And what had we assumed? This is we proved just now. And our assumption is 169 divides x minus 8 times x plus 5 plus 33 and 39, right? Yeah, so this was our assumption. Here, this was our assumption. So now we got from these two statements, we can subtract the first one from the second one, from that subtraction property of divisibility. So that means 169. Okay, Rick joined a bit late, no problem. So 169 divides the difference, so that is 39. This is a contradiction since 169 is greater than 39, it can't divide 39, right? So our claim is proved that 169 can never divide the quadratic x square minus 3x minus 1. So is that clear? Any doubts? Now the last one was a pretty routine problem. We had to we had to prove 18 power 1980 plus 385 power 1980 is not a perfect square. Is not a perfect square. And as a hint, I also provided you a divisor, a prime divisor to check for, that is 13. So the only thing we had to do was to find the set of quadratic residues modulo 13. So for those of you who just joined today's class, like for the first time, so we have covered a number of things actually. I will go over them once again. So we have covered divisibility, and we have covered Euclid's algorithm, and Béjou's theorem, Fermat and Euler's theorem, and even Wilson's theorem. So Wilson's theorem. That's it, nothing more. So we have also covered congruence, of course. So, as a quick summary, congruence is this notation. So this notation here stands for congruence. Congruent. So A is congruent to B when A can be written as some pk plus B. Here k and b are integers and b is less than, no, not necessary actually, b can be anything. So basically when you divide a by b, you get a remainder b and you write it in this fancy format. So that's what congruence is. So when I talk about quadratic residues, I mean, so you see the set of all remainders when you divide by uh, a number p is 0, 1 up to p minus 1, right? So this set is what we call the complete residue class of P, or CRC. And then we derived a smaller class, like not a class, it's another set, which is like 0, 1, and whatever. Uh, I will mention how to derive that. And it's called quadratic residues modulo P. So let's look at the quadratic residues of 13. So for the complete residue class of 13, you have the numbers 1, 2, 3, 0, 1, 2, 3 up till 12, and then you square each of them and then take remainder modulo 13 to get the corresponding quadratic residues. So you square 0, you get 0. You squared 1, you get 1. You squared 2, you get 4. You squared 3, you get 9. You square 4, you get 16. You divide by 13, you get 3 as a remainder. You square 5. So next you squared 5, you get 25. You divide by 13, I guess you get the remainder 12. And similarly, you observe that going like this, you don't need to actually uh, go up squaring each of the numbers, each of the 13 numbers from 0 through 12, since after 6, the number 7, 8 can be written as minus um, -6, -5, and -4, and so on up till -1. Like 12 is -1 here. Whenever you have like 7 is congruent to 7 mod 13, right? You can subtract, like you can add any multiple of 13 on any side, right? The congruence will be preserved. You can just add -13 on right side. It's also a multiple of 13, right? So you get 6, -6. So you know 7 is congruent to -6 mod 13. So it's like a circular group. This complete residue class modulo 13 is a circular group. I won't define what's a group formally, but you get the idea, right? So we just need to check up till 6. Since up till 6, like 6 was congruent to -7. Okay. So yeah, so where am I? Yeah, so we only needed to check up till the first 7 numbers, up till 6. Since after that we are getting the square of of the negative number minus 6, which we already have checked here. See, minus k, when you square it up, you get minus 1 squared times k squared. We have already calculated the quadratic, like whatever k square is congruent to mod 13, right? Just beforehand. And minus 1 squared is just 1, so it won't be contributing anything. So you just need to calculate the first 7 of the remainders. So when you calculate them, you get this set 0, 1, 4, 9. You can write it as minus 4. Is okay. 12, you can write it as minus 1. So 1, 2, 3, 4, 5, 6. You need one more. So what is 6 squared? 6 squared is 36. It's minus 3. So if you rearrange, you get minus 4, minus 3, minus 1, 0, 1, 3, 4. Right. So these are the quadratic residuals on 30. So now we have these two numbers. We just take remainder by 13 and we are done. So what is 18? So we know 18 power 12 is congruent to 1 mod 13. This is Euler's theorem, Fermat's theorem. It says a power b minus 1 is congruent to 1 mod b, but here he had 2 prime and it's prime. 13 here is prime and 39 have 4 prime. So next you take whole power of, first divide 980 by 12. 12 ones are 12. You have 78, it's 6, 72, 65. So it's exactly dividing. So you get 1. So this is what 18 power 1980 gives remainder 1 when divided by 30. Next we have 385. So similarly, 385 power 12 is congruent to 1 mod 13. You take power whole power 165. You get 385 power 1980, which is congruent to um, not 80. 385 power 12 whole power 165 congruent to 130. So our original number 1980, 18 power 1980 plus 85 power 1980 is actually congruent to 2, 130. And as you can see, this 2 is not in this set, so it's not a quadratic residue, so no perfect square can be congruent to 3, congruent to 2 mod 30. This is not a perfect square. Not a perfect square. Now let's discuss the second one, the most difficult of the four. For that, any questions? If there is any question, you don't need to be ashamed. Just ask it on the chat box, so you can unmute and ask this. The second one, the question was, so you have the number 7 power 9999. And oh, so there is a question. Okay, so nice question. So, Manoj asked, how do we know what congruence to take, what modular to take? So basically, you in this kind of problems, you try out with all the well-known modulus. So the well-known uh, on residues modulos are 3, 5, 8, 4, and 13, and 16, and like this. So 3, 5, and 8 are the most important. And 4, 2. 13 is actually pretty rare. So that's why this problem was on the difficult side. But I had given the hint that just look congruence modulo 13. So that made it pretty easy. Okay, so there is no other way than to just trial and error way, finding how to, like, which residue to take. You got it. So now for the second one, we need to find the last three digits. So find the last three digits of 7,999. So I've taken this problem from the book Triangle. I guess I'm having the name here. Ah, that's good. So the name of the book is the author, and the name of the book is Problem Solving Strategies. This book is mostly recommended for students aspiring for math Olympiads and all those exams. Not exactly for SNC entrance. They have pretty. It has many advanced problems, and it doesn't have calculus and other important topics which are important in SNC entrance. So yeah, so it's good for practicing problems if you are like practicing problems. But otherwise, I would recommend you to follow it, like follow the exercises, follow all the exercises, expression, and over this book is called, what is it called? Yeah. There is tomato, there is expression, there is pre-college mathematics. These books are much more. So three digits are 7.999. So you obviously need to take modulo, take mod 1000, right? To get the last three digits. So let's exactly do that. So you first observe the GCD of 7 and 1000 is 1. You can use Euler's theorem. Using Euler's theorem, you get 7 power 5 1000 congruent to 1 more 1000. Euler's theorem. And it's 5 1000 due to the pi is called Euler's quotient function, if you remember. 5 1000 is basically 1000 times 1 minus 1 by 2 times 1 minus 1 by 5. Since 1 and 2 are the only prime factors of 1000. So that is like 400. So you know 7 power 400 is not 1 1 1000. But you need to find this number 7.999. So you can write 7 power 999 times 7 power 1000 by 7. This one going to 7 power 400 whole power 20, 20 or 25 times 7 inverse. The first part is like 1. Here 1 is the second one. To find the, the multiplicative inverse of 7 modulo 1000. For now, 1000 is not a prime number, so the multiplicative inverse of everything that exists modulo 1000. 7 has to be in the reduced rescue class of 1000 or it will have a but you see, 7 is already in the reduced rescue class of 1000. So the city of 7 and 1000. That means first is very able to apply all of the right. That means this inverse exists, whatever it is. So let's try and find it. There are many standard way to find inverses modulo a large device. Like here in this case, it's 1000. For smaller ones, you can use the entire method, but for larger ones, use binomial. Here, let's use differential word and without term. So, from without term, from without term, that the of theorem can be expressed as the linear combination of the two numbers. Here, x naught and y naught can both be negative and positive. There exists x naught and y naught. Of course, these are not unique. For which this happens. So, how would you find the x naught and y naught? But if you were able to find uh, here in this case, P7 and P is 1000. So P is 1, of course. You're able to find x naught and y naught. So that's 7 x naught and 1000 y naught is 1. If you take 1000 on both sides, so 1 will contribute to 7 x naught on 1000. Since this thing goes to 0, this comes to 0. Then x naught is exactly the keywords that we are looking for. Since 7 times x7 inverse is 1, and you can use coefficient comparison to see x naught as well. Okay, so we need to find x naught and y. You can use Euclid's algorithm, like I given exercise last. Most of an example last class to not last class, last to show how to find what such coefficient of results. So basically, what you do is you retrace the steps of finding the ECP. Like, you first use fundamental term arithmetic to say 1000 is equals to 7 times 142 plus 6. Correct? Like, that's divisor of the last step is 7. Divided by 7. 6 times 1 plus 7. That's again 1. step divided by perimeter velocity. Zero. So that's why the equation algorithm is. So now you can easily this. So this is the GCD. This 1 is equals to 7 minus 6. And from here, 6 is 1000, 1000 minus 7 times 1.2. And then this that is 1 times 143 minus 1 times 2. So long as it's a city, it is equal to 7 times 143 breaks not and 1 plus 1000 times minus 1 times 1. And as you know, it's not as the 7 fraction of the law 1000. 7 is 1 to 143 1. So we got our answer. Basically 1. Here we can put this one to 1. Last three digits are 1. That covers for the 4 problems of the last week, the price test. So doubts, questions, queries, this class. So let's check out this one. This is one expression. So let's put that 2 power p plus 3 power p have a perfect power for any time. The voice is good. So prove that 2 power p plus 3 power p is not a perfect power for prime. Here the perfect power means that doesn't exist. So there doesn't exist a such that 2 power p plus 3 power p is equal to p squared. Yeah, is my voice audible clearly? So, try out the problem for 5 minutes. The video then it's pretty obvious. So when it is, use this factorization. Okay, so my voice is breaking. I think it's due to the microphone. So you try the problem. I will try to change my headphone. The hint is x plus y, or should I say x power a plus y power a is equal to x plus y times x power a minus 1 minus x power a minus 2 times y power 1 plus x power a minus 3 times y squared minus 1 up till y power minus 1. This is only true when A is on. So this implies divides x plus y divides x power a plus y power a when A is on. This is called group factor theorem. This is called the theorem. Also has a minus version that holds for all A, not just for odd A. And so this is the minus one. You can use that to solve this problem. So I will change the mic in the meantime. Okay, so now is my voice better audible? So could anyone of you solve the questions? Just a minute. So, okay, yeah, so using my hint, you can obviously understand A is P here, X is 2, and Y is 3. So let's try to factorize 2 power P plus 3 power P. 2 power P plus 3 power P is equal to 2 plus 3 times 2 power P minus 1 plus 2 power P minus 2 times 3 plus dot dot dot. Sorry, not plus. Minus plus minus plus. Sign change is alternated. So the second factor is obviously an integer. So 2 plus 3 is divisible. 2 power p plus 3 power p is divisible by 5. So now we know 2 power p plus 3 power p is divisible by 5. So if 2 power p plus 3 power p has to be some perfect power of k, say suppose k power r, then 5 divides k power r, which implies since 5 is a prime, 5 must divide k. And that implies 5 power r divides k power r, right? So now this has to happen. Right? 2 power p plus 3 power p is to be a perfect square. So now let's see if this happens. So now move on to the next fact. This one, this huge one. You see 3 is congruent to minus 2 mod 5. So we can write the second factor as 2 power p minus 1 minus power p minus 2 times 3 plus dot 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 up till 3 power p minus 1. And this is equal to sum over 2 power p minus 1 minus I times 3 power I, where I runs from 0 to p minus 1. Yeah, minus 1 power I is also there. This is congruent to sum over 2 power p minus 1 minus I times 3 is minus 2, and we can take that minus 2 inside, this minus 1 inside, sorry, we get 2 power I. So this is mod 5. Now, so and simplify it to get this 2 power I and 2 power p minus I, they end up to give 2 power p minus 1. And then you can take 2 power p minus 1 out of the summation notation. Then you or sum up over p things. So you get p times 2 power p minus 1. So you get p times 2 power p minus 1. That is what our number, 3 power, so 2 power p plus 3 power p divided by 5 is congruent to this thing. And this is not 0 if p is not 5 and p is not 0. So
So 5 doesn't divide 2 power p plus 3 power p by 5 if p is not equal to 5. This implies this can't be a perfect square. So 3 power p plus 2 power p is not a perfect square, a perfect power for p not equals to 5. Right. So for p not equals to 5, it has one 5 factor of 5 only, an odd number of factors of 5 only. So it can't be a perfect power. So the only case left is p is exactly equal to 5. So let's check that case explicitly. So if p is equal to 5, we have 2 power 5 plus 3 power 5 is equal to 32 plus 3 power 5 is 81 times 3, 243. We have 275. 275 is not a perfect power, you can check. Right, so none of them are perfect powers. So any doubts, queries, questions? If not, let's move on to the next theorem, Chinese remainder theorem. So this is a very old theorem. Actually, we sometimes unconsciously use this theorem when we were in junior school. There are questions like find the number k such that it gives remainder 2 when divided by 7, remainder 3 when divided by 5, and remainder 1 when divided by 11. And you had a very complicated pseudo trial and error method of finding this number k. It satisfied all these three conditions. That's what we're going to formalize right now. This for Chinese remainder term. So the formal statement is magic expression for that one for this formal statement. So it says let M1, M2, so let me write it down. So M1, M2, M3, these are the divisors up to MR. So there are R of them. So they are positive integers, so natural numbers, and relatively prime. So are relatively prime, that is Mi and Mj. The GCD between Mi and Mj is 1 or I not equals j. And other than these R numbers, there are numbers A1, A2 up till AR. So they are again another R set of numbers. They can be anything, I guess. So these are basically the numbers used in this system of equation, R congruence equations we have. So X is congruent to A1, M1. Another condition is X is congruent to A2 on M2, so on up till X is congruent to AR mod MR. So these are the conditions that X is the number that we want to find. It's unknown. These are the conditions that we have. So X must give remainder A1 when divided by M1, must give remainder A2 when divided by M2, so on up till it must give remainder AR when divided by MR. So following these are conditions. So this is set of R linear congruence relations. So the we sometimes refer to as CRT or Chinese remainder theory. Says there exist solutions. There exists unique solution of the above set of linear congruence modulo product over mi. So basically, it says the above equation, above set of equations have a solution. That is, there exists some x such that they satisfy all r of them, and that x is actually when we take mod, the product of all the devices. That is m1, m2, m1. So let's see the theorem in action. So let's first prove this theorem, I guess, since we will take a middle path. Like we first take an example and try to discover x. Discovering x. So let's go with the example mentioned in the book. So we have three set of equations here. It should give remainder 2 when divided by 4. It should give remainder 3 when divided by 5. And it should give remainder 1 when divided by 7. We need to find x. First see that 4 and 5. The GCD between 4 and 5 is same as that between 5 and 7, which is in turn same as that between 4 and 7, that is 1. First, so the set of conditions that we had are already satisfied. They are relatively prime. So now we can safely proceed to discovering what x is. So the trick here is to consider the product of all the devices. So 4 times 5 times 7, which is 20 times 7 is 140. So we have this product, capital M. And now we kind of find the basis of this system. So I don't want to define what is basis, or since you don't know linear algebra, you can think of it as the coordinate system. So normally we have seen that in XYZ coordinate system, you have like any point in space, you can uniquely identify it as X, Y, Z coordinates. And they are like perpendicular to each other, right? They're perpendicular to each other. So they're set up as perpendicular axes. And these axes can be algebraically denoted by something called a basis vector. So let's see. So here we can define mi, capital Mi, as capital M by small mi times the inverse of this whole thing, mod mi. This is a pretty complicated looking thing, so let's break it down. So capital Mi by small mi, this is an integer. This whole thing. This is an integer since this is equal to m1, m2 up till mi minus 1 times mi plus 1. So we are teaching I, then m right? So the product of all the mi's. We are just dividing mi out, dividing out mi. And then this mi is prime. Sorry, like not prime, it may not be prime, but observe that GCD of mi and capital M by mi This is 1. Why is that so? This is because this second thing contains, since second one just contains everything except mi, and all those things are relatively prime to mi, so they can't have a common divisor, right? Then that common divisor must divide some other mj not equal to I. That means that mj and mi has a common divisor, so that will violate our assumption that they are relatively prime. So mi and m by mi m1, sorry, mi is relatively prime, and that means, so that implies m by mi is inside the reduced residue class of mi. So for those of you who are new today, this reduced residue class is basically a smaller subset of the complete residue class that I defined before. Here, I guess. Yeah, so here. This is a complete residue class. The set of all possible remainders module P or any number for that matter, it's M. The complete residue class is 0, 1, 2 up till M1, Mi minus 1. And the reduced residue classes are all those numbers which are relatively prime to Mi and from this set. So you can see that M by Mi must be in this set since GCD of Mi and M by Mi is 1. So they're relatively prime, so it has to be in this set by definition. And whenever things are in this set, they have an inverse. So this is a corollary of Euler's theorem, or actually it's not a corollary in that sense. This can be proved, and I had proved it previously. I will do it once more. Okay, let me try it now. So should I try it, or I guess I should I will do it after I prove this Chinese remainder theorem, because that will cause deviations and distortions. Let's assume there exists inverse. There exists an inverse of m by mi modulo mi. So now that inverse is what we are after. Let's call it bi. So bi is the inverse, multiplicative inverse of m by mi mod mi. So so that means mi times bi is 1 mod mi. Right. That's the definition of inverse is. You take the product, you get 1. And that means capital Mi that as we just defined it, it's Mi by Mi times Bi, which is 1. So capital Mi is 1 mod Mi. Now let's see what capital Mi is congruent to, not any other Mj. So Mj is not equal to I here. Can you see what Mi is congruent to mod Mj? This is pretty easy since you see what M by Mj is. Sorry, M by Mi is. M by Mi is M1 up till Mi minus 1 times Mi plus 1 times up till Mr. So it has everything except Mi. So that means it also has Mj somewhere. Mj divides M by Mi, right? For all j not equal to I. That's why it's congruent to 0 mod Mj. Bi is just another integer. So whatever you multiply it, it will always be divisible by mj. So mi is 0 mod mj for all j not equals to I, and mi is 1 mod mi. Using these two set of facts, we can try to define x as the sum over capital Mi times ai. I runs from 1 through R. So here in our context, m is 140. And then let's calculate the three mi's. So m1 is 140 by 5, no 5, it's 4, which is 2 3s are 12 and 20 is 5. M2 is 140 by 5, yeah, it's 5. So 5 2s are 10, 40 is 8. And last one is M3, 140 by 7 is 20. Now we have got the mi's. Now x is, uh, so we wanted set of, so we wanted remainder 2. So A1 is 2, A2 is 3, and A3 is 1. So A1 M1 plus A2 M2, sorry, oh, sorry. These are not M i's completely, right? We have to multiply it with B1. So let's find B1 first. So you can use that Euclid's algorithm trick if you uh, rigorously want to find B1. But here, since the GCD, sorry, the devices are small, we can try to hit and run. So 35 is congruent to, if we take mod 4, it's congruent to 3 mod 4. So of course we can take 3, we can multiply it with 3 to get 3 5s are 15, or just, this is 3 and that is 3, so 3 times 3, that is 9, 9 times 9 is 1 mod 4. So we got the inverse of 35, it's 3. So V1 is 3. M1 is basically 35 into 3, so whatever that is, 105. Right. This is M2, this is B2, this is B2. Let's see. So 28 is congruent to 3 mod 5 again. And you can see if we multiply it with 2, we get 3 2 are 6. 6 is 1. So this B2 here is 2. So multiplying 28 with 2, we get 2 8 to 16, we get 156. So M2 is 56. And for the last one, 20 is congruent to 7. So 6 mod 7. So you can take multiply it with 6 and see 6 times 6 is 12. So 6 times 6 is 36, which is 1 mod 7 6. Yeah, 35 is divisible by 7. This is 20 times 6 or 120. So now got we can run into M3. Now we can find x equals A1 M1, A2 M2, M3. A1 is 2, A2 is 3, A2 is 1. So 2 times 105 plus 3 times 2 times 56 plus the 1. Yeah, so 1 times 120. I guess it adds up to 898. Okay. So you found x, right? It's 498. It's obviously not unique. And the number x is not unique, but if you take on 140, that is their product, this is unique. Then let's see what it's mod 140, what it's congruent to mod 140. You can check it's 78. So 140 divided by divided by 140 is 3, 2 zeros equals 78. Why is that this thing is unique mod 140? To prove that it's unique for 140 or m, you see you can assume x naught and x1 are two solutions of the above system of linear congruence. Suppose we have two distinct solutions, such that x2, such that x naught, so they are distinct in the sense that x naught and y naught are not congruent mod 140 or here or in general case, M is the product of the mi's. Now see that x naught has to satisfy all the linear equations, right? The x naught has to be congruent I mod mi. Y naught also has to be congruent to ai mod mi, since they are solutions. And now you subtract them, you get ai minus ai, that is 0. 0 negative mi. Now this is true for all I. Right? And all the mi's are co-prime pairwise, that is mi times mi and mj. GCD between them is I, is 1 for all I not equals to j. Now we know when this happens, we can use this theorem of basic congruence. That if A is congruent to B mod uh, n1 and A is also congruent to B mod n2, that implies A is congruent to B mod LCM of LCM n1 and n. LCM is LCM is basically the product divided by HCF or GCD. Right, so that means x naught minus y naught is congruent to 0 mod LCM of n1, n2, n1. And since they're co-prime, the LCM is their product. So n1, n2, n1, which is n 0 mod. You can take y naught on the right, so x naught and y naught are congruent mod n. That's that ends the proof and shows why they're they're congruent modulo n. So the solution is unique modulo n. So I hope this was clear. Practice one or two problems and then end the class. So if you have any doubts, you can ask right now, or else we have problems. By the way, this formula that first problem, this one, so this one, that the number of prime factors in n factorial is the infinite sum of uh, the floor of the quotients when we divide n by p power I. It is also called the p Polignac. So you don't need to memorize the names, but sometimes naming something helps to remember things. Problems. So, Chinese tournaments or applications. So I guess I haven't discussed problems of this type. So show that there are infinitely many primes. Now we use there is no there the number of prime numbers, sequence of prime numbers don't have an upper bound there. There is nothing called the last prime number, up to which we don't find any prime numbers. So any idea how to prove such things? The trick is to first is we use proof by contradiction. So we are using proof by contradiction. We assume the set of primes is indeed finite. Set of primes called S is finite. So we can then find a capital N, which is the product of all pi's in S. That is, it's the product of all the primes in this set S. this product plus 1. Okay. So we are defining it like this. This sign here is defines in checking out list of negations. It's there. So now let's use properties of divisibility to show this number and indeed has a new prime factor which is different from all these PIs. So let's find that. You see, we have the fundamental theorem of arithmetic draw disposals. So it says there exists a prime factor p such that p divides n. Everything in this universe has prime factors. Okay. Like even a prime number has a prime factor, which is the prime number itself. So let's p be that prime factor which divides n. You see, p like consecutive numbers are co-prime, like a and a plus one. So the GCD of a and a plus one is one. Why is that true? Since GCD of a and a plus one is same as GCD of a and one by Euclid's algorithm. Euclid's algorithm is a plus one minus a, and that is a and one. Of course, a and one cannot have one GCD, that is one. So consecutive numbers are co-prime. You see n that if p divides like that. So I wanted to say p divides n, then p n or n and n minus 1, these are consecutive numbers, so they are co-prime. So this implies p doesn't divide n minus 1 since p divides n. Otherwise, p would have been common between n and n minus 1. Like cd to divide, you get divided by p. That's not that. So p doesn't divide n minus 1, which implies p doesn't divide this product. The product. Let's see, like I S P I. P doesn't divide this product. And let's assume suppose pi is common between should I say then let's find the GCD of p and this product. What is the GCD? So this is one. So it's any prime factor. This thing first thing only has prime factors p1, p2 up to pr, the contents of S. Any one of them can't divide p. So that would mean p is a prime number, right? So p can't be divided by any prime number other than itself. And that prime number p doesn't divide the whole product. So p is only one among the product, right? So p is not inside S. This source p not is not inside S. So that is a contradiction. If we assume the universe of prime numbers were finite and everything is contained in S. So we just constructed a number n, which had a prime factor by fundamental theorem of arithmetic, which is not in S. So from the contradiction, set of finite S is infinite. So set of finite numbers. This was a proof why number of primes are infinite. So that we can try to like prove that the number of prime numbers of the form 4n minus 1 is prime is infinite. We will just specify a form of the prime number. Then we'll ask you to prove it's that form of prime number is also infinite. It's true for any any form in them. It's also the same thing. We just construct n as 4 times p1, p2 up till pr minus 1 step. You see the construction is a bit different than the previous one, but all why are we sticking to this one? Since this one is a proper exact property that like if this has a prime factor p, then that p has to be of the form 4n minus 1. Why is that so? It's, uh, see, this number n is of the form 4n. If you consider this as n, 4n minus 1. Numbers of the form 4n minus 1 are only have factors of the form 4n minus 1. Why is that so? You can consider modulo 4. Taking mod 4, this thing is congruent to minus 1 mod 4, right? And if you see the set of the complete residue class mod 4, this is the complete residue class mod 4, you can rewrite it as minus 2, rewrite it as this form. And now there are 4 numbers in them. There are so many way you can multiply it, you will get. If you consider CRC4 whole square, that is the Cartesian product of this complete residue class modulo 4. So there will be 4 square many terms, 16 terms. Or actually, I'm talking about Cartesian product. You see, I'm trying to see what are the corresponding residues when I check each possible pair of multiplications. Let's start with 0. 0 1 multiplied with itself gives 0, multiplied with 1 gives 0, multiplied with 2 gives 0, and multiplied with minus 1 also gives 0. So 0 always gives 0, multiplied with anything else. Then for 1, we get the whole set again. Yeah, so we get the whole set again. 0 gets 0, 1 gives 0, 1, 2, minus 1. Minus 2 gives, sorry, 2 gives 0, 2, 4 is 1, minus 2 is 2. So it doesn't give minus 1, rest all the things it gives. Minus 1 on the other hand gives 0, minus 1, minus 2 is 2, and this one is 1. So it gives the whole thing, right? Okay, so let's see what ways we can get a minus 1. Either we got minus 1 from here, but if we multiplied 1 with minus 1 to get a minus 1. Or we got minus 1 from here, which is same thing. We multiply minus 1 with 1. There is just one way we can get uh, something congruent to minus 1 mod 4. That is, it can be factorized into two factors, one of which is congruent to minus 1 mod 4 and the other is 1 mod. So you see, always numbers of the form 4 and minus 1 always have a factor. So 4 and minus 1 as a factor of the form 4 and dash minus 1. So that's why we pick this form. That's so that it has a factor that we can say p is of the form 4 and minus 1. The rest of the argument is same as in here. And then we say p is not immense, but p is a prime, and p is of the form 4 and minus 1. So that's a contradiction, and the set of primes of the form p and minus 4 and minus 1 is infinite. And also there's another problem of this code. You have to find n consecutive composite numbers. Find n consecutive composite numbers. Composite numbers are numbers which are not primes. That is like 4 or 12 or 6. Things that are factorizable. So can you quickly find these n consecutive prime composite numbers? It's basically we are using this factorial to generate a point. You see, this factorial is divisible by all the numbers from 1 to n minus n plus 1, right? So we can just keep on adding 1, then 1 again, and so on. So we need n of them. That's why I started with n plus 1 factorial. So these n numbers are consecutive, as you can see. And each one of them is composite. So the first number is divisible by, okay, sorry. We can't take the first number just since one is every prime. So n plus 1 plus n plus 1. That is the last one. So each of these n numbers is divisible by either 2 or 3 or 4 or n plus 1, and they are certainly greater than 2 and 3 and n plus 1. So they are certainly composites. This is just to remember things. Sometimes there are problems when you work by deciding. So it's almost time. So, so proof that there are infinitely many primes. Many primes of the form for n plus 1 is basically the same argument, and also similarly prove there are infinitely many primes of the form 6n plus 1. Third one is uh, proof prove that for each positive integer n, so for all n in capital N, that is natural numbers, for all natural numbers n, there exists n consecutive positive integers, none of which are integral powers. Integral powers primes. That is none of which are perfect power of primes. Like as in this case, these are n consecutive numbers where each of them are composite. You have to prove there for all n there exist n consecutive integers like a plus 1 up to a plus n minus 1 consecutive integers, and for all I, a plus I is not equal to and p power k for all p and p is prime. You will need both Chinese remainder theorem and all the theorems that we have done till now to solve this one. And the last one is p is a prime and p doesn't divide a, and also p doesn't divide b for two integers a and b. Then show that p divides a power p minus 1 and b power p minus 1. That's all for tonight. See you next week. Try to solve the problems from exercises of discussion. If you have any doubts, you can come to me. We can discuss them in our classes. So, okay, so good night, everyone, and bye. Yeah, good night.